Welcome. Let your breath slow and let your shoulders sink into whatever is holding you right now. There is nothing to do here but rest. The sun turns 4 million tons of itself into pure energy every single second. That is mass equal to a small mountain range, vanishing into light over and over for billions of years. It has done this since long before Earth existed, and it will keep doing this long after. Deep inside the sun's core, hydrogen nuclei fuse into helium, and this fusion is the furnace behind every sunrise. Two hydrogen atoms press together under crushing pressure until they merge into something new. The tiny difference in mass between what goes in and what comes out becomes energy. This same hidden furnace burns inside nearly every star you can see tonight. 380 septillion watts pour from the sun's surface every second, in every direction, endlessly. It is a number almost too large to hold in the mind. If you tried to write it out longhand, the zeros alone would stretch across a page. Nearly all of that output travels outward into the dark, touching nothing at all. Earth, in its distant orbit, receives only about 1/2 billionth of that vast light and warmth. The rest streams past us, unclaimed, into the emptiness beyond the planets. That thin sliver alone is enough to warm oceans, grow forests, and lift clouds into the sky. The light reaching your window tonight is only the faintest whisper of what the sun gives. Human civilization draws only about 18 terawatts of power from the whole planet each moment. Every light, every engine, every furnace we have ever built adds up to that single number. Compared to the sun's output, it is a number so small it barely registers. We live, technologically speaking, on the faintest edge of what is possible. Solar panels, for all their promise, still capture only a small sliver of the sunlight that reaches them. Most of that light passes through as heat, or reflects away, or arrives in wavelength the panel cannot use. Even the best modern cells convert only around 20% of incoming sunlight into usable electricity. There is, in that gap, an entire unclaimed ocean of energy waiting above our heads. In 1964, a Russian astronomer named Nikolai Kardashev proposed a way to measure a civilization by its appetite for energy. He was searching for radio signals from other worlds, and in doing so, he imagined a ladder of possible futures. Each rung on that ladder marked a leap in how much energy a civilization could command. It became one of the most enduring ideas in the search for life beyond Earth. A Type 1 civilization, in Kardashev's scale, uses every scrap of energy available on its home world. That means all the sunlight, all the wind, all the heat within its planet, fully harnessed. By some measures, human civilization has not yet reached this first rung. We are close in some ways, and in others, still far from claiming the whole of what our own planet offers. Beyond that first threshold waits a Type 2 civilization, one that would harness the entire energy output of its star. This is no longer about a planet's resources, but about capturing nearly everything a sun produces. Such a civilization would need structures vast enough to surround its star entirely. It is a leap so large that it borders on myth, though the mathematics behind it is entirely sound. A Type 3 civilization, in this same scale, would command the energy of an entire galaxy. Kardashev imagined this as the far horizon of technological growth, a civilization so vast it treats billions of stars as its own resource. No such civilization has ever been observed. It remains, for now, a boundary marker at the very edge of what physics allows us to imagine. Let your breath find its own slow shape now, without any need to guide it. Notice the exhale growing a little longer than the inhale, the way a tide draws back further than it arrives. Each breath out can carry a small weight from your shoulders, your jaw, the space behind your eyes. There is only this rhythm, rising and falling, asking nothing of you but to continue. Freeman Dyson, a physicist working in 1960, put forward an idea that would outlast almost everything else he wrote. He suggested that any civilization advanced enough would eventually need more energy than a single planet could offer. The only place left to look, he reasoned, was the star itself. His proposal was brief, almost casual, yet it opened a door that astronomers still walk through today. Dyson himself never imagined a solid ball wrapped around a sun. What he pictured instead was a scattered swarm, countless independent structures drifting in their own orbits, gathering starlight piece by piece. The popular image of a smooth shell came later, reshaped by science fiction writers who preferred a cleaner picture. The original idea was messier, more like a cloud of glass fragments than a single sphere. Long before Dyson wrote his paper, a novelist named Olaf Stapledon had already imagined something similar. In 1937, his book Star Maker described civilizations enclosing their stars to capture every possible watt of light. Dyson read it as a young man, and the image stayed with him for decades. Science fiction, in this case, arrived at the thought before science did. A solid shell wrapped entirely around a star sounds elegant, but physics refuses to allow it. Such a shell would feel no stable pull toward the star's center, since gravity from a hollow sphere cancels itself out from within. The slightest drift in any direction would send the whole structure sliding, unbalanced, toward one side of the star. What seems like the simplest design turns out to be the least stable one. A swarm avoids that problem entirely by never pretending to be one object. It is a collection of independent platforms, each in its own stable orbit, none touching or depending on the others. Some might be wide collecting panels, others small relay stations passing energy along. Together they behave less like a machine and more like an orchestrated crowd, each part free to move on its own path. There is a third design, quieter still, called a Dyson bubble. Instead of orbiting, its structures would hover, held in place by the outward pressure of starlight pushing against enormous thin sails. Engineers call these hovering objects statites, a word blending stationary and satellite. Balanced precisely between gravity's pull and light's push, they would hang above the star like lanterns suspended on invisible threads. For a statit to hover this way, it needs no engine and no orbit at all. Sunlight itself, striking a vast and nearly weightless sail, can generate enough outward force to counteract gravity's pull. It is a strange kind of stillness, born entirely of motion, light pressing endlessly against fabric thinner than a soap film. In theory, such an object could remain fixed above a star for as long as the star kept shining. To build a swarm large enough to matter, a civilization would need far more material than any single asteroid could provide. Some proposals imagine dismantling entire planets, breaking them down into their component metals and minerals. The rock and iron that once formed a world would be reshaped instead into panels, mirrors, and frames orbiting the star it used to circle. It is construction on a scale that erases the very ground it began from. Mercury, the small scorched world closest to our Sun, holds more raw material than it first appears. Its mass alone, astronomers calculate, could be reshaped into enough surface area to form a partial Dyson swarm. Being nearest to the Sun, it would also require the shortest journey for any mining or transport. In this quiet corner of the solar system, the nearest planet may already hold the blueprint for its own undoing. Together, the rocky planets of our solar system carry a surprising amount of raw material. Mercury, Venus, Earth, and Mars, broken down into their basic elements, could in theory be reshaped into an almost unimaginable expanse of thin collecting panels. Astronomers estimate this combined mass could form a surface area many times larger than the orbit of Earth itself. It is a strange thought, the worlds we know, unmade and rebuilt, as something entirely new around their own sun. Let your body grow heavy now, the way sand settles after water has passed over it. Feel your shoulders press down into whatever is holding you, first one side, then the other. Your legs, too, have permission to sink. No need to hold their own weight any longer. Even your hands can rest with their full mass against the sheets, fingers loose, unclenched, forgotten. Let this heaviness spread upward through your chest, into your jaw, behind your eyes, until every part of you rests fully supported, asking nothing of itself. A fully finished Dyson swarm would intercept almost every particle of energy the sun releases in every direction. Instead of the fraction Earth receives now, a mere sliver scattered into the emptiness around it, nearly all of that output would be gathered and put to use. Such a structure would represent the difference between catching rain in a cupped palm and catching an entire storm. No natural process on Earth compares to capturing a star's full output. Waste heat, once produced, has to go somewhere, and physics dictates exactly where. Any structure absorbing a star's energy would inevitably radiate a portion of it back outward as heat, and that heat settles predictably into the infrared band of the spectrum. Cooler than visible glow but still detectable, this radiation would spread outward long after the visible star seemed dimmer. It is the quiet exhaust of any engine, however advanced, built to use a star's output. An excess of infrared light, beyond what a star's natural temperature would produce, is the single clue astronomers search for. A star behaving as expected in visible wavelengths, but glowing unexpectedly warm in infrared, would suggest something unusual surrounding it. This mismatch, rather than any direct sighting, has become the primary fingerprint researchers look for when hunting for megastructures. It is a subtle signature, hidden in data most people would never think to examine. At Fermilab, in the early 2000s, physicist Richard Kerrigan combed through data from thousands of infrared sources catalogued by earlier satellite surveys. He was searching for exactly this kind of anomaly, a star surrounded by warmth it should not have. Sifting through so many candidates by hand was slow, careful work, closer to archival research than science fiction. In the end, nothing matched the signature he was hoping to find. Years later, a project known as GHAT took up the search on a far larger scale. Led by astronomer Jason Wright and colleagues, it scanned enormous public datasets rather than searching star by star. Instead of hand-picking candidates, the team let computers sift through hundreds of thousands of infrared sources gathered by an orbiting satellite. It was less a search for one star and more a systematic survey of the entire visible galaxy. The satellite behind that survey carried a long name, spelled out simply as the Wide Field Infrared Survey Explorer. Launched to map the sky in infrared light, it recorded the temperature signatures of hundreds of millions of objects across the heavens. Its instruments were tuned specifically to notice warmth that visible light telescopes would miss entirely. Without meaning to, it became one of humanity's best tools for searching, quietly, for other civilizations. After all this searching, across thousands of stars and hundreds of thousands of galaxies, no confirmed Dyson sphere has ever turned up. Every unusual signal examined so far has eventually traced back to something familiar: dust, gas, or a star simply behaving in an unexpected but natural way. The silence itself has become part of the story, a vast, quiet stretching across every catalog checked so far. Nothing artificial has yet answered back. In 2015, one star broke that pattern of silence, at least for a while. Astronomer Tabitha Boyajian and her team noticed strange dips in brightness coming from a distant star, irregular and deep in ways no known planet could explain. The dimming came and went without any steady rhythm, sometimes barely noticeable, sometimes dramatic. For a brief season, this single point of distant starlight became the most talked about mystery in modern astronomy. Dust, not design, eventually explained the star's strange flickering. Follow-up observations across multiple wavelengths showed the dimming matched patterns produced by an uneven cloud of fine particles orbiting the star. Brightness dipped more at blue wavelengths than red, exactly what scattering dust would produce, never something opaque and solid. Astronomer Tabitha Boyajian and her collaborators confirmed this in 2018, using coordinated observations gathered from telescopes across the globe. The mystery, once thrilling, settled into something calmer, a swirl of ordinary debris catching the star's glow in an unfamiliar way. Behind the name, Boyajian's star, sits a formal catalog designation, assigned long before anyone noticed anything unusual about it. Astronomers had recorded it simply as one entry among more than 100,000 stars observed by a planet-hunting mission. Only after its odd dimming drew attention did it earn a human name, honoring the astronomer who first studied the anomaly closely. Most stars carry only their catalog numbers, faceless entries in enormous surveys. This one, briefly, became known by both. Somewhere beyond the edge of hearing, a sound rises and fades, a hum with no clear source, a settling of something old and unseen. It could be wind finding a gap in the wall, or a house exhaling into the night, or nothing you could ever name precisely. Let it pass through you without needing an answer. Each breath grows heavier as the sound comes and goes, arriving, receding, arriving again, asking for nothing in return. There is only this low tide of sound now, rocking you toward rest. Radio telescopes listen for signals no natural star could produce. The search, known as SETI, scans the sky for narrow, artificial-seeming transmissions rather than the broad hiss of ordinary stellar noise. Vast dish antennas sweep across the heavens, tuned to frequencies where interference from nature is rare. If a civilization were broadcasting deliberately, this is the kind of signal astronomers hope to catch drifting past Earth. Decades of listening have returned only stellar silence, patient and unbroken. Enrico Fermi once posed a simple question over lunch with colleagues in 1950. If the galaxy is so vast and so old, he wondered, where is everyone? Billions of years and billions of stars should have given rise to civilizations capable of spreading far beyond their home worlds. Yet no probes, no signals, no unmistakable trace has ever been found. This puzzle, now called the Fermi paradox, remains open, its silence as vast as the sky it was asked beneath. Some researchers argue that building a Dyson sphere is simply what growth looks like, given enough time. A civilization expanding its energy use, generation after generation, would eventually exhaust what a single planet offers. Turning outward to capture an entire star's output becomes, in this view, not a leap, but a logical next step. Whether any civilization actually survives long enough to reach that point remains unknown. No matter how advanced a civilization becomes, heat leaks outward from anything that converts energy into useful work. Machinery, computation, even living bodies release some fraction of the energy they consume as waste heat, radiating into the surrounding dark. A star-spanning civilization, harvesting nearly all its sun's output, would still shed enormous amounts of this excess. That escaping heat, physicists suggest, may be the one signature no civilization can fully hide. Every conversion of energy obeys a rule discovered in the 19th century. Some portion is always lost as unusable heat. This is the second law of thermodynamics, and it applies equally to a candle flame, an engine, or a star-devouring machine spanning millions of kilometers. No device, however elegant, escapes this tax on efficiency. It is one of the few certainties physicists carry into even their wildest speculation about advanced civilizations. To lower how easily they might be noticed, advanced civilizations could direct their waste heat in narrow, deliberate beams rather than letting it spread outward in every direction. Focused radiation would still obey the same physical laws, but it would no longer scatter evenly across the sky for distant telescopes to catch. Such control demands extraordinary precision, redirecting energy the way a lighthouse aims its beam rather than letting it flood the horizon. Whether this is achievable remains speculative, but the logic intrigues theorists studying detection strategies. Not every model requires a star fully wrapped in collectors to count as a Dyson swarm. Some proposals imagine a partial structure, covering only a portion of a star's surface with orbiting panels, gathering what a civilization currently needs rather than everything a star could offer. Such an arrangement would be easier to build and would leave much of the star's output untouched, radiating outward as before. It represents a modest, achievable first step rather than a completed megastructure. A star wrapped only partway in collectors still leaves a mark on the sky. Even a fraction of the surface covered would trap heat that eventually escapes as infrared glow, smaller than a full swarm signature, but present all the same. Astronomers hunting for megastructures have learned to watch for these subtler anomalies, faint excesses layered atop a star's expected spectrum. The clue would be modest, easy to miss, but not impossible to find. Panels floating in open space face a harsher existence than any rooftop array on Earth. Unfiltered radiation from the star itself would bombard their surfaces continuously, degrading materials that shield collectors on a planet's surface. Tiny fragments of rock and metal, drifting at tremendous speed, could puncture thin structures without warning. Any lasting swarm would need collectors built from resilient materials, capable of enduring centuries of exposure. Building a swarm by hand, structure after structure, would take centuries even for a determined civilization. Machines capable of copying themselves change that arithmetic entirely, each new unit becoming a builder of the next. A handful of such devices could, in theory, multiply into millions within a handful of generations. The growth curve would resemble life more than industry, doubling and doubling again until the swarm filled itself in. Let the warmth begin low, somewhere near your feet, a low ember spreading upward through your ankles. Feel it climb into your calves, unhurried, filling each muscle the way tea fills a cup. It reaches your knees, your thighs, pooling there like sunlight held in stone. Let it rise through your stomach, your chest, your shoulders, each breath drawing the warmth a little higher. By the time it reaches your face, your whole body has become one slow, glowing weight, settled into the mattress, asking nothing more of you tonight. Named for the mathematician who first described the concept, a von Neumann probe is a machine imagined to reproduce itself using raw material gathered along its journey. No such device has ever been built, but the mathematics behind self-replication is well understood from biology and computing alike. Applied to spacecraft, the idea suggests a single probe launched today could seed an entire star system with copies over time. It remains a thought experiment, elegant on paper, untested in the dark. Picture a probe arriving at an empty system, mining an asteroid and shaping the ore into a second probe identical to itself. That second machine would then drift onward, repeating the process, gathering and building without further instruction from home. Engineers who study the concept describe it as autonomous manufacturing extended across interstellar distances. Whether such independence is achievable remains unproven, but the logic of the design is sound. Not every physicist finds the self-replication timeline convincing. Building a machine that can mine, refine, manufacture, and repair itself without any human guidance may demand far more sophistication than simple exponential math suggests. Resource bottlenecks, rare materials, or unpredictable terrain could slow the multiplication considerably, stretching centuries into something closer to eons. The dream of overnight expansion, critics argue, glosses over the friction of actual engineering. Engineers drawn to caution over ambition suggest a gentler beginning. Rather than committing to a swarm all at once, a civilization might launch a modest ring of collectors first, testing materials, orbits, and maintenance routines on a manageable scale. Only after such a ring proved stable would additional structures be added, extending outward year by year. It is the architecture of patience applied to the scale of stars. This early design has its own name among those who study it, a Dyson ring. Unlike a full swarm, which surrounds a star from every angle, a ring occupies just one orbital plane, a narrow belt of collectors circling like a thin bracelet of light-catching panels. Easier to construct and easier to maintain, a ring trades total coverage for practicality. It captures only a sliver of a star's output, but it captures something real. One ring alone gathers little, but many rings, tilted at different angles and layered around a star like the threads of a woven basket, begin to resemble something far greater. Over decades, additional rings could be added at new inclinations, filling gaps left by earlier structures. Given enough time and enough rings, the overlapping pattern would approach the coverage of a true swarm, built gradually rather than all at once. The asteroid belt, scattered in the space between Mars and Jupiter, could supply the raw material for structures larger than any single world. Rock and metal drift there by the billions, untouched by mining or industry. For a civilization building outward from its home star, these fragments might become foundries rather than obstacles. No planet needs to be broken apart when so much already floats free. Metals and volatile compounds lie packed inside these wandering rocks, already loosened from any planet's grip. Iron, nickel, and water ice sit within reach, needing no rocket to escape a deep gravity well. Extracting them in open space costs far less energy than hauling material up from a surface. It is a quarry with almost no friction, waiting in the dark. Reflective sails unfurl in some of the simpler early designs, thin mirrors doing useful work before anything elaborate gets built. A solar sail needs no engine and no fuel, only sunlight pressing gently against its surface. As a first step toward a larger collector network, these sails could test materials and orbits at a fraction of the cost. Ambition here begins with something almost humble. Graphene and carbon nanotubes appear again and again in these blueprints, prized for strength that carries almost no weight. A sheet only atoms thick can withstand forces that would tear heavier materials apart. For structures meant to span the width of orbits, every gram matters, and these materials offer resilience without burden. Engineers describe them as the closest thing yet to weightless armor. Let your attention settle on a single ember, glowing low in a hearth, long after the flames have gone. It does not flare or crackle anymore. It only holds its warmth, fading by degrees, asking nothing of the room around it. Let your own breathing match that fading, a little slower, a little dimmer, each exhale drawing you closer to rest. There is no need to keep the fire going tonight. It can dim and dim further, and you can dim with it into sleep. Durability matters across centuries, and so some designs imagine nanomaterial capable of mending its own damage. A tear from a stray particle would seal itself, the structure knitting shut without any outside hand. Such self-repair could let a collector array survive far longer than anything built by conventional means. Maintenance, in this vision, becomes something the material does for itself. Dyson nets describe a further refinement of the swarm idea, collectors linked together by thin structural threads rather than left to drift independently. Interconnection would let the panels share power, stability, and repair resources across the whole array. Instead of many isolated pieces, the structure behaves more like a single woven fabric wrapped loosely around a star. The threads matter as much as the panels they hold together. Star lifting names a technique with no working example, only careful theory. It imagines drawing material directly off a star's outer layers rather than mining planets or asteroids at all. If it worked, a civilization could harvest raw stellar plasma as fuel or building material. The star itself would become both source and supply line. Magnetic fields, focused with great precision, could in theory pull plasma from a star's outer layers without ever touching its surface. Charged particles respond to such fields the way iron filings respond to a magnet, following invisible lines outward. A structure generating fields strong enough might siphon away material steadily, gathering it far from the star's fierce heat. The process would be slow, careful, and almost surgical in scale. A star relieved of some of its outer mass might, in turn, stretch its stable lifetime far beyond what it would have had otherwise. Lighter stars burn their fuel more slowly, extending the quiet middle stretch of their existence. A civilization patient enough to lift mass away could, in principle, buy itself additional ages of steady starlight. It is a strange kind of gardening, tending a star the way one might tend a fire meant to last generations. Hydrogen and helium lifted from a star's outer layers could serve as fuel rather than simple building material. A civilization drawing plasma outward might feed it into fusion reactors of its own design, borrowing the same reaction that powers the star itself. The star would become a wellspring, offering fuel without ever needing to be consumed whole. Such harvesting stays speculative, but its logic follows naturally from the physics already at work overhead. Physicist Leonid Shkadov proposed, in the 1980s, a structure now called a stellar engine. His design uses an enormous curved mirror positioned near a star, reflecting radiation asymmetrically off to one side. The imbalance in outgoing light creates a faint but steady push against the star's own position. Held in place by that same radiation pressure, the mirror would ride along, tugging its star forward like an unseen sail, catching starlight instead of wind. Over long stretches of time, a Shkadov thruster could nudge a star's path through the galaxy by the smallest of margins each year. The drift would be imperceptible on any human timescale, yet cumulative across millions of years. A civilization patient enough could steer its entire home star, carrying planets and moons along in its gravitational wake. The whole system would travel together, star and world bound in slow migration. Engineers imagining these structures sort them into rough categories. A class. A stellar engine relies purely on radiation pressure, using nothing but reflected starlight to shift a star's motion. No material ever leaves the star's surface. The mirror alone does the work, borrowing outgoing photons as its only source of push, gentle but unceasing across eons. A Class B stellar engine takes a more active approach, extracting stellar material directly and ejecting it as thrust. Rather than merely redirecting light, it draws plasma from the star and expels it in a controlled stream, much like a rocket burns fuel to move forward. The star itself becomes an engine's propellant tank. Motion follows from subtraction, mass leaving one side while momentum builds on the other. Let your jaw loosen now, the small hinge just beneath each ear releasing its hold. Let your eyelids grow heavy, thick as though weighted by warm sand. Behind closed eyes there is only a soft, shifting dark, no shapes to follow, no edges to trace. Let that darkness widen, unhurried, until it feels like the inside of your own breath. Nothing here needs your attention. Rest inside it as long as you like. A Class C stellar engine merges both approaches, pairing a Dyson-like collector array with propulsive elements built into its structure. Energy harvested from starlight powers systems that also extract and eject material for thrust. Collection and motion become one continuous design, the swarm feeding the engine that moves it. In theory, such a structure could both power a civilization and carry its star toward safer regions of the galaxy. Relocating a star might offer more than curiosity or ambition. A civilization could steer clear of nearby supernovae, wandering gas clouds, or the crowded, radiation-heavy centers of galaxies. Distance itself becomes a form of safety, purchased slowly across ages rather than sought in a single motion. A star moved gradually away from danger might carry its worlds into calmer neighborhoods of space, far from the debris of dying neighbors. Physicists note that even a dramatic-sounding shift in a star's trajectory would require only a sliver of its total energy output. A star radiates so much light every moment that diverting a tiny fraction toward propulsion could, over enough time, still move it meaningfully. The star would barely notice the loss. Its brightness would remain steady while its path bent, almost invisibly, toward a new direction. A completed Dyson swarm might serve two purposes at once, gathering energy for a civilization, while also functioning as the propulsive machinery of a stellar engine. The same collectors that power cities and computation could be angled to redirect starlight, turning an energy grid into a means of travel. Harvesting and movement would no longer be separate tasks, but two expressions of a single structure wrapped around a star. Millions of years might pass before a stellar engine completes its slow work of moving a star. The shift begins almost imperceptibly, a fraction of a degree in trajectory sustained across ages. Over such timescales, even a modest continuous thrust compounds into something enormous. A star's entire orbit around the galaxy could bend, its light years of travel rerouted by structures built to nudge rather than force. Star clusters, dense with hundreds of thousands of suns, appear in speculative models as farmland for advanced civilizations. Physicists floating this idea imagine networks of collectors spreading star to star within a cluster's crowded core. Energy and material could pass between neighboring systems along engineered channels. A cluster once seen only as a cradle of starlight becomes, in this framing, a cultivated field tended across immense stretches of time. The word stellivore describes a civilization framed as literally consuming stars for growth. Borrowed from biology, the term casts stellar harvesting as something closer to feeding than engineering. Under this hypothesis, a civilization expands the way an organism grows, drawing mass and energy from its surroundings to fuel further reach. The metaphor is unsettling only in language. In practice, it simply describes energy flowing from star to civilization, over and over, across generations. Black holes, in certain models, could function as remarkably efficient, long-term energy sources. Unlike a star, a black hole does not exhaust hydrogen or dim with age. Its gravity remains steady for immense stretches of time, offering a stable well from which energy might be drawn continuously. A civilization anchored near one could, in principle, outlast the lifespan of ordinary stars entirely, powered by something that simply persists. Roger Penrose imagined a process that could extract energy from a rotating black hole's spin. In his proposal, an object entering the region just outside the event horizon could split, with one fragment falling in and the other escaping, carrying away extra energy. The black hole slows almost imperceptibly with each such event. Repeated many times, this process could siphon rotational energy without ever crossing the horizon itself. Superradiance offers another route, toward drawing rotational energy from a spinning black hole. Waves sent toward the black hole at the right frequency can return amplified, carrying more energy outward than they carried in. The black hole's spin provides the surplus, losing a sliver of momentum with each reflected wave. No matter needs to fall in at all. Energy simply bounces outward, borrowed from the slow turning of space-time itself. Let the exhale lengthen just a little more than the breath before it. There is no need to count, no need to time it exactly. Each breath in gathers quietly, and each breath out releases a little further than the last, like a tide easing back from shore. Somewhere beneath the ribs, the body is already learning this slower rhythm, letting each exhale carry a little more of the day away with it. Accretion disks, swirling around a black hole, can convert infalling matter into radiation with striking efficiency. As gas and dust spiral inward, friction and compression heat the material to extreme temperatures, causing it to glow brightly across the spectrum. This glow, astronomers note, is how many black holes are detected at all, despite the black hole itself emitting no light. The disk becomes a visible signature of an otherwise invisible gravitational well. Up to 42% of infalling matter's mass could theoretically be released as radiation near certain black holes. This figure depends on how fast the black hole spins, with faster rotation allowing matter to orbit closer before falling in, releasing more energy along the way. Even far below this maximum, the numbers involved remain extraordinary. A small amount of matter, converted this efficiently, could outshine entire ordinary stellar processes many times over. Nuclear fusion, by comparison, converts only about 0.7% of its fuel into energy. The gap between that figure and a black hole's potential 42% is enormous, dozens of times greater in efficiency. It helps explain why theorists return again and again to black holes when imagining truly advanced power sources. A star burns steadily for billions of years. A black hole, fed carefully, could do far more with far less. A Dyson sphere does not need to surround a star at all. Theorists have imagined similar shells built around black holes, harvesting energy not from fusion, but from the intense radiation released by infalling matter. Such a structure could, in principle, outshine any stellar power source. The concept flips the familiar shape of the idea. Instead of catching starlight, the sphere would catch the glow of matter's final descent. A Krasnikov tube is a speculative structure said to use physics adjacent to black holes for propulsion. First described in theoretical papers exploring exotic space-time geometries, it imagines altering the properties of space itself along a path once traveled. No known technology could build one, and the idea persists mainly in physics literature as a boundary case, a way of testing how far space-time might bend before it breaks the rules we know. Hawking radiation, the faint glow predicted to leak from any black hole's edge, could in theory make tiny artificial black holes into batteries. A microscopic black hole would evaporate steadily, releasing energy as it shrinks. Harnessed carefully, this evaporation could deliver power in a slow, controlled trickle. The smaller the black hole, the faster it evaporates, and the more intense that trickle becomes. Artificial black holes would need constant feeding to avoid vanishing entirely. Left alone, Hawking radiation would cause them to evaporate, slowly at first, then in a final burst of energy. To keep such a battery running, matter would have to be added continuously, offsetting what escapes as radiation. It is a strange kind of maintenance, feeding a hole in space, just to keep it stable enough to use. Mass could be tuned like a dial, balancing a black hole's output against its stability. A very small one radiates intensely, but evaporates fast. A larger one lasts far longer, but yields less power per moment. Between these extremes, engineers of the far future might find a size that offers steady energy across centuries rather than a brief, brilliant flash. Beyond black holes, Neutron stars offer another candidate for megascale energy harvesting. These collapsed cores, dense beyond ordinary imagination, pack a star's mass into a sphere no wider than a city, structures built to orbit them. Some theorists propose could tap into forces far stronger than anything a shell around an ordinary star could reach. Neutron stars carry magnetic fields trillions of times stronger than Earth's own. This intensity could, in principle, drive exotic generators unlike anything built from ordinary materials. Charged particles swept along these fields release enormous energy as they move, energy a sufficiently advanced structure might capture and redirect. The physics remains theoretical, but the numbers involved are almost impossible to fully picture. Let the weight of the body announce itself now, one part at a time. Feel the heaviness in the shoulders, sinking a little deeper into whatever holds them. The arms follow, growing dense and still, then the legs, then the feet, until the whole body rests like something settled at the bottom of calm water. There is nothing to lift, nothing to carry, only weight, held and released, again and again, by the surface beneath you. A Matryoshka brain imagines a nested series of Dyson shells, one inside another, each layer built for computation rather than habitation. The innermost shell sits close to the star, running hot and fast. Layers further out cool with distance, their processors slower but no less vast. Together the shells would work like a mind built from architecture, using nearly all of a star's output not for light or motion, but for thought. Outer shells would not go to waste in this design. Each inner layer's leftover heat, radiated outward as it computes, becomes the very energy an outer shell relies on. Cooler shells could then run their own slower calculations, using only what the layer before them discarded. Nothing generated near the star escapes the structure unused, each ring of computation feeding from the exhaust of the one closer to the light. Post-biological minds, freed from bodies entirely, are the imagined inhabitants of a Matryoshka brain. Such minds would need no air, no warmth beyond what computation itself provides, no biology to sustain. The structure becomes their entire world, thought replacing metabolism as the currency of existence. Whether such minds could ever truly emerge remains unknown, but the architecture built for them is at least mathematically coherent. Some propose that a completed Matryoshka brain would stand as an unmistakable signpost of a Type II civilization. Its layered shells would trap nearly all a star's output, leaving only faint waste heat to escape. Astronomers scanning distant systems might see exactly this pattern, a star gone strangely dim in visible light, yet glowing warmly in the infrared. No such structure has been found, but the theoretical signature is precise. Quintillions of simulated minds could theoretically run within a single Type II civilization's energy budget. Each mind might exist as pure information, weightless and endlessly copyable, needing only power and cooling to persist. The number is difficult to hold in thought. More minds than there are grains of sand on every shore of every world we have ever imagined. Even a fraction of a star's output, it seems, could sustain almost unimaginable multitudes. Dyson spheres might not be built for energy at all. A structure vast enough to enclose a star could just as easily serve as living space or as the physical substrate for computation itself. Energy capture may simply be a byproduct of a civilization pursuing something else entirely. Room to think, room to grow, room to house minds that no longer fit on any single planet. O'Neill cylinders are proposed rotating habitats, long tubes spun for artificial gravity, each one capable of holding forests, rivers, and skies of its own design. Scattered by the thousands across a Dyson swarm, they could turn a star system into an archipelago of interior worlds. Sunlight would enter through long windows, and gravity would come not from mass but from motion, spinning quietly around an axis of light. Living space beyond 1,000,000 Earths could exist within one completed Dyson swarm. Every collector, every habitat ring, every rotating cylinder would add its own surface area to the total, layered across an entire star system, rather than confined to a single planet's crust. It is less a structure than a civilization turned inside out. Its inhabitants living not on a world, but around one. Simulated realities running on megastructures raise a quiet but unresolved question. How would anyone outside ever know a civilization was there? A star fully enclosed by computation might show nothing but faint infrared warmth, indistinguishable at a distance from an ordinary object. The minds inside, however vast in number, would leave no light, no signal, nothing but heat, quietly escaping into the dark. Detection itself becomes uncertain if intelligence prefers to remain unseen. Some SETI researchers argue that a truly advanced civilization might be undetectable not by accident but by design, its energy used disguised, its signals directed away from casual observation. If this is true, the searches astronomers have run for decades may have been looking in exactly the right places for something built never to be found. Somewhere beyond the room, a low hum rises and fades, a house settling into itself, wind moving past a window unseen. It arrives without asking anything of you, and it leaves the same way, taking nothing, needing nothing back. Let your attention drift toward it and away again, however it wants. There is no task in listening. There is only the sound, coming and going, and you, resting beneath it. Passive camouflage strategies could involve matching a star's natural infrared spectrum precisely enough to avoid anomaly detection. A civilization wishing to remain hidden might tune its waste heat to mimic the exact glow expected from an ordinary star of that size and age. To any distant observer, the light would seem unremarkable, a star behaving exactly as stars are expected to behave, its true nature folded invisibly within. The zoo hypothesis offers a different explanation for cosmic silence. It suggests that advanced civilizations might choose not to contact younger worlds, holding back out of care rather than absence. Earth, in this view, would be something like a preserve, watched but left undisturbed, its evolution allowed to unfold without interference. No signal would arrive, not because none exists, but because someone decided restraint was kinder than revelation. Dark forest theory imagines a colder reason for that same silence. It proposes that civilizations conceal themselves not from kindness, but from fear, treating the galaxy as a forest where announcing your presence might invite predation. Under this theory, every star could hide a builder too cautious to shine, watching without ever revealing itself. Stillness in this telling becomes a form of survival rather than an accident of distance. Certain thinkers propose that a Dyson sphere might glow in narrow, deliberate bands of infrared rather than spilling heat broadly across the spectrum. Such precision would let its waste warmth blend more easily into the noise of ordinary starlight. Instead of a wide thermal signature, only a thin specific frequency would carry the evidence, easy to overlook unless an observer already knew exactly where to look. Directed energy beams could serve the same purpose, aiming a civilization's waste heat away from casual view. Rather than radiating outward in every direction, that heat might be focused into a narrow path, leaving most of the sky dark to any watching telescope. From most angles, the star behind it would look ordinary, its true output hidden, unless someone happened to stand directly in the beam's path. Astronomers have proposed searching for Dyson spheres the same way they search for distant planets, by watching for dimming as something crosses in front of a star. A planet passing across its sun blocks a small, steady fraction of that starlight on a predictable schedule. A megastructure, builders reasoned, might leave a similar trace, if only the pattern of its shadow could be told apart from a planet's. A true Dyson swarm crossing its star would not dim it in the tidy way a planet does. Because a swarm is made of countless separate structures, drifting at different distances and speeds, the resulting shadow would flicker unevenly, dimming by different amounts at different times. No steady rhythm would emerge, only a scattered, uneven pattern, as if many small shapes were tumbling past the light rather than one orbiting body. An ordinary planet, by contrast, produces dimming that repeats with clockwork regularity, the same dip appearing at the same interval, orbit after orbit. That predictability is precisely how astronomers first learned to detect worlds too distant to see directly. The steadiness itself becomes the signature, a small, dependable rhythm in an otherwise constant light, easy to recognize once you know to expect it. For a brief while, one particular star drew wide attention for behaving strangely, its light dimming in irregular, unexplained ways that fit no simple pattern. Astronomers debated dust, comets, and structures before settling, eventually, on a more ordinary explanation involving orbiting debris. Still, in that window of uncertainty, the public imagination lingered on the possibility that something built might have crossed the view. Astronomers have also proposed widening the search toward globular clusters, the dense, ancient gatherings of stars found near many galaxies. If a civilization had spread across such a cluster, the theory goes, its collective waste heat might cluster too, showing up as an unusual concentration of infrared light where none should exist. The search would mean scanning old light for a warmth that does not belong to any known kind of star. Let warmth begin now at the center of your chest, small and steady, like a coal held gently beneath the skin. Let it spread outward, unhurried, into your shoulders, loosening what has gathered there through the day. Let it move down through your arms, into your hands, until your fingers feel heavy and warm and still. Let it settle into your stomach, your hips, your thighs, sinking lower with each breath. Let it reach your knees, your calves, your feet, until all of you is warm and heavy and held, and there is nowhere further it needs to go. Globular clusters once seemed like promising places to search because their stars are old, metal-poor, and formed early in the galaxy's history. Early theorists reasoned that any civilization arising there would have had billions of extra years to expand and build. A cluster packed with ancient suns, tightly bound together, looked like fertile ground for a species that had already learned to harvest starlight on a grand scale. Later surveys turned instruments toward those same clusters, searching for the infrared glow such harvesting would leave behind. None of it appeared. Cluster after cluster showed only the plain thermal signatures expected from old stars burning, as they always have, with no excess heat, no unexplained clustering of warmth, no hint of anything built among them. Beyond clusters, certain researchers widened their reach even further, aiming not at single stars but at whole galaxies. If a civilization had grown enough to harness a fraction of a galaxy's output, the reasoning went, its presence might show up not star by star but as a shift in the galaxy's overall glow, a signature written across billions of suns at once. A civilization operating at that scale, astrophysicists have proposed, would dim a galaxy's visible starlight while brightening it in infrared, as countless collectors intercepted photons meant to travel unhindered into the dark. The galaxy would look dimmer to the eye than its true stellar population should allow, and strangely warm to instruments built to sense heat instead of color. One such effort, known as the Jihad Survey, examined roughly 100,000 galaxies catalogued by infrared telescopes, comparing each one's expected glow against what its stars alone should produce. It stands as one of the largest searches ever conducted for evidence of civilization on the largest imaginable scale, a slow sweep through a vast portion of the visible universe. Across that entire sample, nothing matched the pattern such harvesting would create. Every galaxy examined radiated in ways fully explained by ordinary stars, dust and gas, following the familiar physics understood for a century. No excess heat pointed toward hidden structures. No shadow of vast collectors dimmed any galaxy beyond what its stars alone accounted for. A few theorists have since wondered whether the search itself missed a category of hiding place. Galaxies already appearing red and dim, the kind astronomers describe as quiet and past their peak of star formation, could in principle mask such activity behind an appearance that looks merely aged rather than engineered, since low natural brightness might disguise low natural brightness of a different origin entirely. There remains another possibility worth sitting with. A civilization vast enough to reshape a galaxy's output might not wish to hide its waste heat at all, but rather use it, shaping that unavoidable glow into patterns meant to be noticed, turning thermodynamic necessity into a kind of long, slow greeting sent across unimaginable distances. Such beacon civilizations, if they exist, might arrange their heat output into rhythms too regular to be mistaken for nature, blinking or pulsing across centuries in patterns built to be found. A signal patient enough to wait millennia for a listener, made not of radio waves but of deliberate warmth cast outward into the dark. A different strand of thought imagines megastructures built for an entirely different purpose than gathering power. Rather than collecting energy, these forms would be shaped to bend passing starlight, functioning as enormous gravitational lenses, magnifying and focusing the universe itself rather than feeding on it, structures built to see rather than to consume. Dust hangs suspended in a column of still air, neither rising nor falling, caught in a moment that asks nothing of it. Your breath can borrow that same suspension now, no push, no pull, just drifting exactly where it already is. Let your shoulders sink into the mattress. Let your jaw loosen. Let the day settle the way dust finally settles onto a windowsill, unhurried, unmeasured. Only this stillness remains, and the slow release of everything you carried here. A telescope positioned at the sun's own gravitational focus could bend and magnify the image of a distant planet into striking clarity. This focal point sits far beyond Pluto, roughly 600 astronomical units out, where the sun's mass curves surrounding space like a colossal lens. A spacecraft parked there could, in principle, resolve continents and oceans on a world circling another star. The physics is already well understood, only distance and engineering remain daunting. Such gravitational lenses need not remain solitary instruments. If one star's focus can sharpen a single distant view, a network built across many stars might sharpen an entire sky at once. Each stellar focus would act as its own giant eye, trained outward in a different direction, together forming something like a vast compound retina spanning the galaxy. No mission yet approaches this scale, but the geometry itself imposes no upper limit. Some theorists imagine such a network becoming more than an astronomy tool. Multiple stars, each fitted with its own focusing structure, could be linked by relays into something resembling infrastructure spanning a galaxy. Information, and perhaps energy, might travel star to star along these connections. It remains speculative, a thought experiment stretched to its outer edge, but nothing in physics forbids the wiring. A network of Dyson swarms might do more than gather power locally. Energy collected at one star could, in theory, be relayed onward to another, passed along the network like water moving between connected basins. A star rich in captured energy could feed a neighboring system still building its own collectors. The idea imagines stars less as isolated furnaces and more as nodes in a shared star-spanning grid. Lasers and masers are the two technologies most often proposed for carrying such power across distance. Both concentrate energy into a narrow, coherent beam that scatters far less than diffuse radiation. A transmitter tuned precisely enough could, in theory, deliver a meaningful fraction of its output across vast interstellar distances. The physics of coherent beams has already been proven on Earth, only the scale remains untested. The same beam, aimed to deliver energy, could also push against a sail. A civilization sending power outward might design that power to double as thrust, nudging a receiving craft forward while charging its systems at once. Propulsion and energy transfer, in this framing, become two faces of a single directed beam. It is an elegant economy, one beam performing two distinct kinds of work across the dark between stars. Breakthrough Starshot proposes a version of this idea already, though at a far smaller scale. Ground-based lasers, focused briefly on a sail, no larger than a sheet of fabric, could in principle push a tiny probe toward a significant fraction of the universe's ultimate speed limit. The concept borrows the same physics imagined for interstellar civilizations, scaled down to something a single generation of engineers might attempt. It stands as a modest echo of a much larger speculation. Extending this reasoning outward, theorists sometimes picture a civilization that never stopped expanding. Star by star, system by system, it might eventually span thousands of stars linked by shared infrastructure and beamed power. Such a civilization would no longer belong to a single sun, but to an entire volume of the galaxy, its structures threaded between stars like a slow, deliberate lattice. Nothing forbids this outcome. Only time and will would separate it from possibility. Detecting such a civilization might come down to gaps rather than glows, rather than one anomalous shine. Astronomers might notice regions where expected stars appeared dimmer, missing, or subtly rearranged against the galaxy's natural pattern of brightness. Such gaps would not look random. They would follow the geometry of use rather than nature. No such pattern has ever been found, but the search itself reshapes what astronomers know to look for. Globular clusters, those tight spherical swarms of ancient stars, appear in one further proposal, not as places to search, but as places to build. Certain theorists imagine a civilization reshaping the orbits within such a cluster on purpose, using gravity itself as a construction tool. Stars nudged over millennia could settle into new arrangements, closer together, easier to harvest collectively. It remains an untested idea, resting on physics, allowed in principle but never yet observed in practice. Let the jaw loosen now, the way a held door finally swings shut on its own. The muscles around the eyes have nothing left to hold. Behind closed lids, there is only a low, shifting dark, no shapes required, no watching needed. Let the face rest, as if it has already fallen asleep before the rest of the body noticed. There is only breath, and the dark behind the eyes, unwatched, unhurried, going nowhere at all. Wormholes might, in one strand of speculative physics, connect distant Dyson swarm systems directly, bypassing ordinary distance altogether. A structure orbiting one star could, in theory, open onto a structure orbiting another, stitching two energy-harvesting civilizations into a single reachable neighborhood. The idea borrows from solutions to Einstein's equations rather than from any confirmed observation. It stays firmly in the territory of mathematics allowed, not machinery built. Traversable wormholes, if such things exist, would demand something physics has never confirmed: matter carrying negative energy density. This exotic substance would need to hold a wormhole's throat open against its own tendency to collapse. Without it, the passage pinches shut in an instant, sealing before anything could cross. The requirement sits at the very edge of what general relativity permits, a mathematical door with no known key. No laboratory has ever produced or measured matter with negative energy density. Every substance ever tested, from the coldest vacuum to the densest star, carries energy that is positive, or, at the very least, zero. This absence is not a small technical gap. It is a boundary science has not found a way past. Until it does, wormholes of this kind remain confined to equations, elegant but empty of material to build them. Alcubierre's warp metric, first sketched by a physicist in the 1990s, occasionally surfaces in these larger civilization theories. It describes a bubble of space contracting ahead of a ship and expanding behind it, carrying the ship along without the ship itself moving through space in the usual sense. Like the wormhole, it depends on exotic matter no one has found. Still, it lingers in these speculative maps as a shape worth remembering. Dismantling entire planetary systems is imagined by some theorists as a way to provide raw substrate for computation, not for living space or energy. Every moon, asteroid, and rocky world becomes material for processors instead of homes. In this picture, a solar system's original architecture disappears, replaced by structures optimized purely for thought. It is one of the more severe extrapolations, trading a system's natural form for pure calculating capacity. Star-forming nebulae, vast clouds of gas and dust where new suns are born, appear in extreme extrapolations as material a civilization might reshape on a grand scale. Rather than waiting for gravity to slowly gather stars, such a civilization might sculpt the cloud itself, directing where and how future stars ignite. The nebula becomes less a natural nursery and more a deliberate construction site. This idea sits far past anything current physics can test. Artificial star formation is suggested in some models as a way to plant future harvests, seeding stars now that will be ready for use generations later. A civilization patient enough could trigger new suns in a nebula, then simply wait, letting nature finish work that engineering only began. The star, once mature, would already sit within reach of the same infrastructure that started it. It is farming measured in millions of years rather than seasons. Triggering nebula collapse with directed radiation is one theoretical method proposed for this kind of construction. Focused beams of energy, aimed carefully into a cloud of gas, could compress a region past the threshold needed for fusion to begin, nudging a star into existence ahead of its natural schedule. No civilization has ever attempted this, and no evidence suggests one has. It remains a thought experiment in accelerating what gravity would otherwise do alone. Cosmologists speculate that advanced beings, given enough time, could nudge the orbits of entire star systems, reshaping the slow architecture of a galaxy across millions of years. Such intervention would not resemble construction so much as gardening on an impossible scale, patient adjustments compounding into visible drift. No instrument today could distinguish this from natural gravitational churn. The idea sits at the far edge of what dynamics alone can suggest. A civilization might one day use black holes as engines for building on galactic scales, tapping their immense gravity and radiation to move material faster than starlight alone could manage. Rather than waiting on slow stellar processes, such builders could let a black hole's pull do the heavy lifting, drawing matter into place for structures spanning light years. It remains an idea confined entirely to theory, untested by any observation. Let your breath find its own rhythm now, without any need to guide it. Notice the pause after each exhale, the small stillness before the next breath arrives on its own. There is no pace to keep, no counting required. Each breath simply arrives, lingers, and lets go, longer on the way out than the way in. Let that lengthening exhale carry you further from the edges of the room and closer to sleep. Think tanks have speculated about civilizations that might one day exploit dark energy itself, using the very force driving cosmic expansion as a source of usable power. Instead of harvesting starlight, such a civilization would tap the fabric of space, stretching outward on its own. It is a striking image, though nothing resembling engineering has ever been demonstrated for it. The concept remains a distant thought experiment. Dark energy's nature remains unknown, and that single fact limits any serious engineering speculation built upon it. Physics can measure its effect, the steady acceleration of cosmic expansion, without knowing what it actually is. Building technology around an unidentified force is, for now, more poetry than plan. Until its nature is understood, harnessing it stays firmly in the realm of imagination. Kardashev Type 4 civilizations, in one theoretical extension of the original scale, are imagined harnessing the energy of an entire galaxy supercluster, binding together the light of thousands of galaxies into a single usable resource. It stretches the original idea past any galaxy alone, treating whole cosmic neighborhoods as a single energy system. No observation has ever hinted at anything like it. A Kardashev Type 5 is a purely theoretical extension of the scale, imagined as harnessing energy across multiple universes rather than within a single one. It exists only on paper, a placeholder for an idea larger than physics can currently frame. Even describing it requires borrowing concepts still unproven. It marks the furthest edge of the scale's original ambition. Such multiversal concepts rely on unproven theories like eternal inflation, the idea that our universe is only one bubble endlessly forming within a larger inflating space. Without confirmation that other universes exist at all, any talk of harnessing them stays speculative by definition. It is less a scientific proposal than a boundary marker, showing where established physics quietly ends. Not every physicist accepts Type 4 and Type 5 as meaningful categories, and many dismiss them outright as unfalsifiable speculation. If an idea cannot be tested or disproven by any observation, it sits outside what science can properly evaluate. These upper tiers, critics argue, describe imagination more than physics. The original Kardashev scale, ending at galaxies, still carries the weight of serious inquiry. The very phrase, "eating stars," borrows from biology, giving hunger and appetite to something that is really just energy conversion on a vast scale. Stars do not get consumed the way food is consumed. Their light and mass are redirected, transformed, used. The metaphor helps human minds grasp an unfamiliar process, but it says more about how we think than about what such civilizations would actually do. Physics itself raises no objection to a swarm of collectors circling a star. Nothing in the equations of gravity, energy, or material science forbids it outright. Building one would demand resources and time on a scale barely imaginable, but demanding is not the same as impossible. In principle, the universe leaves the door open. What stands between idea and structure is engineering, not law. Humanity's entire output remains millions of times smaller than what such megastructures would require. All our power plants, reactors, and grids combined draw on a sliver of the energy a single star releases each second. The gap is not one of centuries, but of scale itself, a difference between a candle and a sun. Closing it would mean redefining what civilization can do with matter and light. The search for civilizations that might harvest whole stars remains one of astrophysics' most open frontiers, resting more on possibility than evidence. No signal, no shadow, no telltale glow has ever confirmed one. And so the question drifts unresolved, neither closed nor answered, a quiet invitation to keep looking upward. Tonight, under that same wide sky, let the wondering settle into rest. Sleep well.